Hey class, so this PowerPoint we're going to talk about series circuits. All right, let's get right into it. Okay, so series circuits, the definition of a series circuit is one complete path for current to flow. So the key word here is one, only one complete path for current to flow. The reason this is important is because when we get to parallel circuits, you'll see that there's more than one, so two or more paths for current to flow. That's the definition of a parallel circuit. So for here, we're only looking at one, real basic. We're looking at a starting point and an ending point, okay? As always, there has to be some sort of electrical load involved in the circuit, along with a switch, a fuse, wiring, items like that. We've already talked about these items, but again, we have to start with the battery. So we start from the beginning. Battery power source. So these two pictures here show a battery. The one on the left shows a 1.5 volt battery. The one on the right just shows a symbol for a battery, but doesn't show, how many volts the battery is. So what we'll do is, from a starting point of the power side, the voltage will come out onto a conductor, go all the way around the conductor, and go through a resistor. In both of these images here, we have two resistors that are in a row, meaning the electricity does not flow left or right, or doesn't flow another way except into the second resistor. That's what this means. That's what series means, is that these two resistors are in a row. They are connected to each other. Okay. So on the next slide here, we have the laws of series circuits. So Kirchhoff's laws apply to series circuits and to parallel circuits. The three here, you guys need to write these down. All right. You need to remember them. You need to understand them. These are the basics of how electricity flows and how electricity works. These are the rules that we have to follow. That's why they're called the laws. Okay, Kirchhoff's laws. So let's look at number one. Number one, the sum of each individual resistors equals total resistance. So we still have to find E, I, and R, like we do with Ohm's law, but we also, in a series circuit, need to find total resistance. Okay. So in this instance here on the right side here, we have a circuit that's 120 volts. The conductor comes out, goes through the first resistor, which is 20 ohms, then goes through the second resistor, which is 40 ohms, then goes back to ground. Okay, so the current will flow through both resistors. In order for us to find total resistance, according to law number one, we need to add. Okay, the word sum means to add. So we're going to add 20 plus 40, and that'll give us 60 ohms. 20 plus 40 is 60. So the total resistance in this circuit here that we're looking at on screen is 60 ohms. Okay, so that's our R. Now let's go to law number two. The sum of the voltage drops equals source voltage. Okay, the sum, I'll repeat it, the sum of the voltage drops equals source voltage. So our source voltage is given here is 120 volts. That means that each resistor, so the 20 ohm or the 40 ohm resistor, they're going to take some of the voltage of the 120 that is available to us. Now, how much each of them is going to take is going to be determined on the resistance of each load, electrical load or electrical resistor. All right, so we're not going to get into that just yet. What we want to understand is that regardless of how much voltage is taken by each resistor, it has to add up to 120. So if the first resistor, the 20 ohm resistor, took, say, 60 volts, the other resistor, the 40 ohm resistor, has to take 60 as well, because 60 plus 60 is 120. The first one couldn't take 50, and the second one couldn't take 200, because 50 plus 200 does not add up to 120. Okay, so the voltage drops have to add up to 120 to make the math work. So in this instance, the 20 ohm resistor would probably take 40 volts, and the 40 ohm resistor would probably take 80 volts. 40 volts plus 80 volts is 120 volts. Okay, so that's how we would get to that number. Now, if we look at the last law for Kirchhoff's law, amperage is the same throughout the entire series circuit. Okay, so let's determine amperage in the circuit real quick. So we have 120 volts, we have 60 ohms of total resistance. 120 divided by 60 will give us 2, and that is 2 amps. Now, if we measure 2 amps on the power side of the circuit, right as it comes out of the battery, we will measure if we measure amperage at the power side of the circuit, we will measure 2 amps. If we measure amperage between the two resistors, we will also measure 2 amps according to the law. And now if we measure amperage on the ground side of the circuit, so that's after the 40 ohm resistor, going back to ground, according to the law, we should also still measure 2 amps. And once we do that, once this is true. So if we were to measure a circuit of this nature and we were to set it up on, say, an electrical board and do a test on it and measure amperage with a digital multimeter, it would work. It would work out. The math would work out. The numbers would work out. Okay. If we were able to replicate this circuit in real life, we would get 2 amps all the way through at the beginning of the circuit, between the two resistors, and at the end of the circuit. So the amperage, which is the flow, again, does not change throughout the entire circuit. Okay. The voltage drops, it moves. The voltage gets used by the resistors as it goes through, because that's the pressure that's pushing through. Then the resistors is what's using that voltage. Okay. But the amperage, which is the flow, the volume of electricity going through the circuit, does not change. It stays the same. Okay, so in order for us to find resistance, voltage, or amperage in a circuit, we definitely have to understand how these series circuits add up, how we get total resistance, amperage, and voltage. Okay, again, usually voltage is given. In this instance here, this picture we're looking at, we have a 12-volt battery. So we have a 12-volt battery. We have a 1 ohm resistor coming out. That's the first resistor coming out of the positive terminal. Then that 1 ohm resistor is connected to a 2 ohm resistor. And then this 2 ohm resistor goes back to ground. Okay, in this little basic circuit, there's no switch, there's no fuse. Obviously, if this was really set up on a car, it would have to have a fuse and a switch. We understand that portion of it already, I hope. But this circuit here that's just set up is just set up just for our purposes of understanding. All right, so we have 1 ohm and 2 ohms of resistance in the circuit, and it is a series circuit because there's no break between any of the wires. It follows one path of electricity to flow. Now, to get total resistance, all we do is add up these two resistors. So 1 plus 2 gives us 3. So our E is 12, our R is 3. Using those two numbers, using Ohm's law, we can find what I is, or amperage. Now 12 divided by 3 is 4. So that will give us 4 amps. Okay. But in order for us to find the total resistance, we need to add up the resistors. Okay, it's pretty simple. This is not a complicated circuit. When we get to parallel, it does get a little bit more complicated. All right, so let's look at this one. Hopefully, at this point, if you want to go ahead and pause the video real quick, please do so. Because we are going to find total resistance in this circuit. So we always find the 3 things, E, I, and R. So E is given, it's the battery voltage, and that's 12 volts. I is not given, so we can't find that yet. And then R is not fully given, but we have 3 resistors in the circuit we're looking at, and we can find total resistance rather quickly. If we go back to law number 1 for the series circuits, excuse me, the law number 1 tells us that we need to add the resistors. So we have 3 ohms, 2 ohms, and 1 ohm. If we add all those up together, that'll be 6 ohms. So 12 volts divided by 6 ohms will give us 2 amps. And that's exactly how we would find the amperage in the circuit. Okay. Now, here's a definition. So definition of a voltage drop is voltage used or voltage lost. Okay. So the main things that use voltage in a circuit are resistors. In this case here, this picture we're looking at, the bulb is the only resistor in the circuit. So if we have a 12-volt battery, the bulb should be using almost all 12 volts. Now, resistors, fuses, switches, wires, those items do use voltage, but the bulb is the main electrical load that should be using the voltage. Okay, and since we only have one here, it should use almost all voltage. You should use up to 12 volts that we have available to us. In reality, will that really happen? No, it won't. It will use as long as it's a good circuit, it will use 11.95 volts, let's say. Okay, but it will use almost all of it. Now, voltage drop that is called, the voltage that is being used is called the voltage drop. Okay, there's also another way to use the term voltage drop, which is voltage lost. If we have a bad ground, so if the ground circuit over here, I would say at the end of the bulb is bad or not connected properly, we would lose voltage on that ground circuit, and that would be lost voltage, not used voltage, because in essence, it's not being used by the bulb, which it should be. So the bulb could be using possibly 9 or 10 volts, and we'd be losing 2 to 3 volts on the ground, on that loose ground. Okay, so voltage drop is voltage used or voltage lost. Now, if we come here and we're looking at this circuit here, so we have a 12-volt battery, we have a 2-ohm resistor, then we have a 4-ohm resistor, and then we have a 6-ohm resistor. And these are all wired in series, because if we follow the path from the power terminal of the battery, it goes out into bulb number 1, then bulb number 2, then bulb number 3, and then back to ground. There's no breakage in between any of the bulbs. It follows all the way through one path for electricity to flow. So, and the resistance values are given. So we have 2, 4, and 6. Again, if we refer to law number 1 for series circuits, that tells us to add up the resistance values. So 6, 4, and 2 gives us 12. That's 12 ohms of resistance. So that's our R. Our E is 12 volts. Now, 12 divided by 12 gives us 1. And that is our amperage. 12 volts divided by 12 ohms will give us 1 amp. Okay, that's how we would find amperage in this circuit. This slide here is talking about voltage drop. Okay, so voltage drop. Let me move myself real quick if I can. All right, there we go. Voltage drop again refers to the voltage lost or voltage used. Now this circuit here, it's a 12-volt circuit, like all of our circuits that we're going to be using for the most part. We have voltage going through the first resistor, which is a 2-ohm resistor. Then we have voltage going through the second resistor, which is a 4-ohm resistor. Now, if we refer to law number 2 for series circuit, the voltage drops need to add up to 12 volts. Okay, it needs to add up to the source voltage. And in this case, our source voltage is 12 volts. So 8 volts and 4 volts does add up to 12 volts. It's not split evenly because the resistors are not split evenly. The rule of thumb here is the higher the amount, the higher the resistor number, or the bigger the resistor, the more voltage it's going to take in the circuit. And it doesn't matter if it's placed in, on the power side or the ground side. Wherever the highest resistor is placed within the circuit, it will take the most voltage, no matter what. Okay, it doesn't have to be first or last or second or middle. It will take the most voltage. Okay. Next slide. All right, dynamic versus static tests. So this is something that will refer to you as a technician or you as a student taking or testing voltage or testing resistance or testing amperage on a live circuit. All right. So voltage drops are dynamic tests. Checking resistance is a static test. But what does that mean? What is static and dynamic? So dynamic means that the circuit is on, it's live, it's working. Okay. We want to test things when they are dynamic, when they are on. We can't check things if they're off as well. All right. Checking resistance is a static test, meaning that we're checking the circuit or checking the component when it's off and when no electricity is flowing through the circuit. That's not a very good way of testing things. So checking resistance on circuits or checking resistance on bulbs, resistors, motors, is not a very good test. In automotive, we don't do that very much. We'll do it here and there a little bit just to verify that something maybe does work. At least we got a good resistance value. Okay, checking that tells us that it's probably at least a connection there. There's something, there's continuity. But checking voltage or checking amperage that is a dynamic test, meaning that the circuit has to be live, has to be working, has to be on. Those are the better types of tests. So anytime we do a voltage drop, that's one of the better tests. That tells us a lot. That tells us how much voltage is getting to the component. Now, in a normal car, if you do a voltage drop on any component in your car, on any light bulb, on any motor, you should be getting 12 volts. The whole car gets 12 volts. So if you're not getting 12 volts, then that's a problem. Why isn't it getting 12 volts? If it is getting 12 volts and it's still not working, then we're not looking at a loss of voltage or um, not enough voltage. We're looking at something else, some sort of maybe mechanical resistance, some sort of I don't know, possible open circuit, maybe. We're looking for a different problem, but we want to do voltage drops and amperage tests as much as possible because that's our dynamic test. That tells us that the circuit's working or not working, and we can only do those tests when the circuit is on. Okay. All right, so let's get to a couple um, uh, circuits here that we can do some calculations on. Now, this is this is the exact same circuit as the previous, I think it was 2 slides ago. Now this circuit here, we have 12 volts and we have 2 amps and we have a total of 6 ohms. Okay, this also gives us the voltage drops on each resistor. Normally we wouldn't have to find that necessarily. We could, but to do the calculations to find E, I, and R, we don't have to find the voltage drops. It's always good to find to understand what's going on in the circuit, but it's not always necessary. Let me get to one here, this next one. Okay, this one here. Now this circuit here, we are looking for R2. So they gave R1 is given, amperage is given, but voltage is given, but the resistance for R2 is not given. This is a series circuit with 2 resistors in it, but we only have the value of 1 resistor. So we have 12 volts, we have 3 amps, but we don't have our total resistance. So how are we going to find this? At this time, this would be a good point to stop the video, pause it real quick, try and figure this out, and then come back. Okay, so I'm going to find this right now real quick. So 12 volts and 3 ohms. How can we do this? Can we find RT right away without doing any other calculations? If you can't see it, we can definitely do it. Okay, so we're going to take 12 volts, and we're going to take 3 amps, because that's what we have. And we're going to divide 12 by 3, and that's going to give us 4. So 4 equals RT, or total resistance. But according to Kirchhoff's law number 1, the sum of the resistance values equals total resistance. So 4 is our answer, but 4 equals R1 plus R2. So if we work backwards, 3 plus what equals 4 will give us our answer. So 3 plus 1 will equal 4. So R2, therefore, is 1 ohm of resistance. Okay, here's another one. This one here, this one has 3 resistors in it. And we are missing the value for R3. Okay, so now if you can, go ahead, please, and pause the video and try and work through this problem yourself, and then come back, and then I'm going to go over it right now. Okay, so we have 12 volts. We have 2 amps. So all I'm looking at right now is the 12 volts and the 2 amps. I am not looking at anything else. Okay, so 12 volts and 2 amps will give us 6 ohms of resistance. So 6 ohms of resistance. Now 6 ohms equals R1 plus R2 plus R3. So R1 is 3, R2 is 1, and R3 is we don't know. So 6 equals 3 plus 1 plus 2. Okay, so R3 has to be 2 because 2 plus 1 plus 3 is going to equal 6 for us. Okay, so R3 is 2 for us to find the right answer. Let's go to this one here. We're just going to do 2 more, and then that'll be the end here at this presentation. Now this one here, we're looking for voltage. We are not looking for a resistance value. We already have them. So all 3 resistors in the circuit, they are given the value of them. So we have 1 plus 1 plus 1, which will give us 3. and we have 4 amps throughout the circuit. Notice how the amperage is shown 4 times. That doesn't mean we add them together. That just means that's telling us that the amperage is the same throughout the circuit. We refer to Kirchhoff's law number 3 for series circuit. That tells us that the amperage is the same throughout the circuit. So we have 4 amps, we have 3 ohms of resistance, and if we do basic Ohm's law, E over IR, 4 times 3 will give us 12, to 12 volts. There we go, the last one. Okay, again, go ahead and pause the video here, and then try and work this problem out yourself, and then come back. So we have 12 volts. We don't know amperage, and our amperage is the one that is not given. Then we have 3 resistors. We have 2 ohms for resistor 1, 2 ohms for resistor number 2, 2 ohms for resistor number 3. So 2 plus 2 plus 2 is 6. So we have total resistance of 6. We have 12 volts. 12 volts divided by 6 ohms will give us 2 amps. Okay, and that would be 2 amps throughout this entire circuit. It would be 2 amps out of the power side, in between resistor 1 and 2, in between resistor 2 and 3, and on the ground side. Okay, amperage again does not change throughout the circuit. Okay, so I hope everyone learned a little bit about series circuits. Be sure to look at the other videos that are available to you regarding series circuits. Okay, if you have any questions, as always, please contact me. Thank you very much.